Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 22, Organic Chemistry 2. Today we will continue covering aldehydes and ketones, chapter 4, oxidation of these molecules. We have covered that aldehydes, unlike ketone, are easily oxidized to carboxylic acid by common oxidants such as bleach, sodium hypochlorite, chromic permanganate, and peroxy acid. Aldehydes with oxidizing agent turn to carboxylic acids. As an example here, butanol with chromic acid give butanoic acid. Cyclopentane carbaldehyde with mild oxidizing agent like silver oxide in tetrahydrofuran water mixture gives cyclopentane carboxylic acids. Silver ion, silver 1, oxidizes aldehydes selectively in a convenient functional group test for aldehydes. The Tollens test involves addition of solution of silver ammonia complex called Tollens reagent ammoniacal silver nitrate to the unknown compound. If an aldehyde is present, you can see clearly after warming up in water bath silver ion transferred to metallic silver like mirror or black suspension. So here propanol with Tollens reagent ammoniacal silver nitrate in basic media, you get the salt of propanoic acid. To get the free acid, you have to add acidified water. And from this reaction, you get the deposition of silver 0 metal. The oxidation of aldehydes can be performed with a mild oxidizing agent like Fehling reagent. It's basic solution of copper sulfate. It's blue in color. When react with aldehyde, transfer this to carboxylate, and copper 2 became copper 1. Copper 1 oxide is red precipitate. So we turn from blue solution clear, and we get a solution with red precipitate of copper 1 oxide. Predict the major products of the following reactions. This compound has two function groups, secondary alcohol and aldehyde. Silver oxide is mild selective oxidizing agent, will oxidize the aldehyde to carboxylic and the OH untouched, and give black or mirror of silver 0, silver metal. The same compound, under the action of chromic acid formed in situ from a mixture of potassium dichromate sulfuric, will oxidize the secondary alcohol as well as the aldehyde, and we get this compound. The secondary alcohol will be ketone, aldehyde will be carboxylic acid. Baeyer-Villiger oxidation of aldehydes and ketones. The ketone RC double bond O R prime are oxidized by Baeyer acid or peroxy acid or hydrogen peroxide to give RCOO2R, given ester. On the other hand, aldehydes RCHO are oxidized under the same conditions to give carboxylic acid RCO2H. So we have ketone with peroxy acid to give ester and carboxylic acid. aldehydes with peroxy acid will give carboxylic acid, and again the peroxy acid will be carboxylic acid. For ketones, it can be viewed as an insertion of O into the C bond adjacent to the carbonyl. For non-symmetrical system, there is selectivity issue to be aware of. Which R group, which CC bond that the oxygen will get in. For the more likely H. So if you have an aldehyde, it will be carboxylic acid because H will be carbon H bond. The oxygen will be inserted in there. Then tertiary alkyl, cyclohexyl, secondary alkyl, benzyl, aryl, primary alkyl, methyl is less likely. This is described as migratory aptitude of the group and relates to ability of the group to stabilize positive charges, which means that the group which is going to migrate should have high electron density on it. That's why it's tertiary alkyl, since you have 3 R group pushing the electron toward the center carbon, makes it electron rich. Let's look for the mechanism of this reaction. Carbonyl and peroxy acid, and the peroxy acid has 3 oxygen atoms. I label this one red in color. So this oxygen, the one red in color, will act as a nucleophile and adds to the carbonyl carbon, forming this species, then followed by proton transfer to this oxygen, leaving the one red now free, and this oxygen will have the positive charge. The 2 electrons, the negative charge, 2 electrons in here, will move to form double bond, eject R prime with 2 electrons to support this oxygen. So the migration, let's say we have said R prime will go to O, red in color, and break this bond to form a double bond in here, and the double bond will be single bond. So the peroxy acid will be carboxylic acid, and the ketone will be an ester. Once again, the ketone will react with the peroxy acid oxygen, the one in red, and this oxygen will add as a nucleophile to the carbonyl carbon, forming this ionic species. Minus H plus H, which we call proton transfer, will leave the red oxygen neutral, and this oxygen will have the positive charge. The negative 2 electrons from this oxygen will go down to form double bond, kicking the R prime with 2 electrons move to oxygen, the one red. OO bond will cleave to form a double bond, and this double bond will be a single one to form an ester. Remember once again, this oxygen, this one. Treatment of cyclic ketone with a peroxy acid yields a cyclic ester. Here we have the carbonyl, we have carbon, carbon, right and left. This molecule is symmetric, so anyone can do, so oxygen will get inserted in here to form lactone, 7-membered ring. Here we have the carbonyl, we have methyl, and we have secondary butyl. Well, so this one will migrate. It has an R configuration. It will migrate with no change, without change in the configuration to get R butyl acetate. So the oxygen will get inserted in here. This molecule, carbonyl is here, we have methyl group in here, we have secondary carbon in here, so this one will migrate, right? And the oxygen will get in here according to our mechanism, forming this ester. Okay? The ester will hydrolyze with base. We give here OH to this carbon and H to that oxygen without changing the configuration on this carbon to get this alcohol. Baeyer-Villiger oxidation is preferred over the epoxidation of double bond. So we have molecule like this. We have carbonyl, which react with peroxy acid to form ester, and also we have another function in here, alkene, which reacts with peroxy acid to form epoxide. Which one is faster? If you used one equivalent, metachloroperoxybenzoic acid, the epoxidation will be favored, and the oxygen will get inserted in here. So we have that ester. If we hydrolyze the ester with base, again, we break in here, we add here OH, and in presence of base that will be carboxylate, and here we get an H. Okay, that's nothing will happen to this carbon configuration and this one. This is down and this is down here, so we can write it in 2 dimensions this way. Predict the major products of the following reactions. Carbonyl is here, peroxy acid, so we will have an ester. Which one will migrate? This is CH2 and this is secondary. Of course, we'll say this one will migrate over this one, and the oxygen will get inserted in here. Well, which one? In this one, no, that's not. This one, it's double bond and then O and then carbon with no changing in configuration. Here we have a change in configuration. This is wrong. And this is the other way around. So this is wrong. So the correct will be structure number 2. Once again, here we have carbonyl. We have here peroxy acid. We call it peroxy monosulfuric acid. In presence of disodium phosphate, here we have CH2 and we have here secondary carbon. So this one will migrate, right, over this one. and the oxygen will get inserted in here without changing in the configuration of this carbon. Well, this is one, yes, that inserted in here. No, this is wrong. This one, oh, we have CH2 in here. It is wrong. That's okay. Number 3, we have oxygen in here between this and this carbonyl. That's right. Then we have CH2. We have, okay, the methyl group. So this is okay. This is changing in configuration on this carbon. This is wrong. So the answer is number 3. 2-phenylcyclohexanone is treated with isotopically labeled Baeyer acid as shown below. Choose the correct product formed in this reaction. This is one is the isotopic oxygen, and we have mentioned clearly in the previous uh, slides that this oxygen is the one getting inserted. So it's inserted in here because this one is secondary and this is CH2. So we are expecting this oxygen to be in here. Oppa, this is correct. This one is in here, wrong. This one is up, but the oxygen is not the correct one. This is wrong. This one again, the oxygen is this one here. No. So the correct structure is number 1. See you next lecture.